Okay. Sorry, guys, we got cut off in the last video. My 15 minutes was up. So let me back up just to remind you something. Okay, so we were saying about circular orbits or darn near circular orbits, that this is the velocity for that object to stay in orbit, not go too slow and crash down, but not go too fast and escape that gravitational pull. All right, so with that, if we now apply some old circular stuff, if you recall, well, the first equation in circular motion was v equals 2 pi r over t, where 2 pi r is the circumference of the circular path. Well, if we solve that for t equals 2 pi r over v, and if we take this new formula in this section and for v expression and plugged it in here, we get a new expression for t based on this speed of an orbit, so orbit v. And this is just another way to clean it up a little bit more. It really means the same thing. There are two different ways to write it. Just condensing the r's through a little bit of algebraic manipulation. So that's some different forms of a formula for the period of a circular orbit, remembering there is a time it takes to go around once. All right. So also have an equation for the total mechanical energy while in a circular orbit. In the last section, we gave a formula derived from the negative integral of the law of universal gravitation, which gave us the potential gravitational energy for situations with things in orbit. And remember, not only we have potential energy, but if this thing's in orbit, it's moving and has kinetic energy. And this is a formula derived for that total mechanical energy, we called it. We learned a time ago that total mechanical energy was the total of any kinetic and potential at any given moment. So for an object in orbit, this expression is total mechanical energy. And prior to an object being fired into orbit on Earth's surface, if it was just sitting at the surface of the Earth, the r would just only be the radius of the Earth, because we have no extra altitude to add to that. And if we haven't fired it yet, the kinetic energy would be zero. So that means that the total mechanical energy at the surface is equal to that same, just the gravitational potential formula, section 12.3, specifically written with the r being the on the surface of the radius of the Earth to its center. So in that case, the work required to place a satellite in orbit is the total energy in orbit minus the energy at the surface. Comes from a manipulation of an old work formula that we had in a prior chapter. So a lot of this stuff, has its little tweaks, but really comes from things learned in the past. All right, so now knowing these formulas, we are going to look at example 12.6 in your book. This is on page 396. So that it says, suppose you want to place a 1,000 kilogram weather satellite into a circular orbit 300 kilometers above the Earth's surface. What speed, period, and radial acceleration, remember radial means centripetal, must it have? Let's start there. What we know, the mass of it. Now remember, it said 300,000 meters above Earth, right? The surface of the Earth. So that's not that R value until we add it to the radius of the Earth, which, remember, we said is, if you don't recall that value, you could look it up. You look it up anywhere, but there should be a table on the last page, a couple pages of your textbook. But adding that with the actual radius of the Earth in meters, we would R of 0.68 times 10 to the 6 meters. So plugging that in for R, plugging in the mass of the Earth is 5.97 times 10 to the 24th kilograms times G, which again is 6.67 times 10 to the negative 11th. Running those numbers, this object would have to bring a velocity of 7,000 3,720 meters per second in order to orbit 300,000 meters above the Earth's surface. Now that we know that, we could plug that V into one of the period formulas from above, and that would mean it has a period that would represent the time it takes to go around one complete revolution of 1,440 seconds. And it brought back another old thing. Like I said, remind you while reading the problem, radial acceleration means it's centripetal, and our core equation way back when for that was V squared over R. Take those two, the V from part A divided by the R we calculated up here, and it would have a radial or centripetal acceleration 8.92 meters per second squared. Let's go on and see what part B has. How much work has to be done to place this solar satellite in orbit? Again, I just saw work equation, so we will need the total mechanical energy at the surface and in orbit, like the equation states. So finding those two through the formulas above, plugging in numbers for total mechanical energy of the orbit yields this value, negative 2.98 times 10 to the 10th of joules. Remember, energy is in joules. And finding it at the surface of the Earth is negative 6.25 times 10 to the 10 joules. So just an FYI, remembering that this value includes both kinetic and potential. This is only the potential because it's not moving at the surface. Subtracting those numbers through the work formula gives 3.27 times 10 to the 10th joules. And I'm not really concerned about part C in the problem. You now have enough information to go and work on some problems from these sections.